Engineering Dynamics Session 3, Kinematics of a Particle. Let's attempt more example on a kinematics of particle to make it more clear. So in this example, example 2, if it's the calculation of a projectile velocity. So if we shoot a bullet into a deep ocean, we want to know how far it travels. Our bullet, how far it's travel, and what is the velocity after a while. So let's go through the problem statement. A small projectile is fired vertically downward into a fluid medium. That's a with initial velocity of 60 meter per second. Due to drag and resistance of fluid, experience a deceleration of a acceleration is a function of velocity, as you can see here. Acceleration is a function of a velocity, meter square seconds, and we want to determine the bullet's velocity and also its position 4 seconds after you fired it. So let's attempt the problem. So that's again a condition that acceleration is a function of velocity. If you can categorize them, you can work them very easily. So acceleration is a function of velocity in SI unit, and as we know, acceleration is a change of velocity over time. So if we just simply take dt here and replace a over here. So that gives us a integration of dv, which is here. Integration of dv over, if you take this part in denominator, it's just dv over a negative 0.4 v cubed from initial velocity, then integrate it to whatever velocity it reaches at the end. And it's equal to, if you take dt over here and integrate it from 0 to t dt. And if you solve this integration, it just gives you a something 1 over, for example, x, a negative x cubed. So that one, the coefficient, it just directly comes out of the integration, and integration of 1 over a x2, that's a negative 1 over 2 times 1 over v2 from a initial velocity to whatever velocity, and in terms of a time span of t. If you replace that in the equation, it gives you 1 over a positive 0.8 is a 1 over v squared minus 1 over 60, which is a squared, which is the initial velocity of the when you fire the bullet, and is equal to times. So that if you want to rearrange the equation based off v squared and then solve it for v, it just gives you a 1 over v squared is equal to 0.8 times t plus 1 over 6 to the power of 2, and that's a yes. And if you just reverse the equation, it just gives you v squared is the same term but to negative 1. So v over v is equal, then v velocity is equal to this function. And if v squared is equal to a negative 1, and then if you square root it, that gives you v of a negative 1 of 1 a half in terms of meter per second. And then if you replace it in terms of times equal to t seconds, mhm, it just gives you a velocity of point a almost 56 meter per second downward. Mhm. I was doubting if the problem statement was for t is equal to 4 seconds or 3 seconds. So if that was the case, you can just replace a t is equal to 4 seconds in this equation, just in case that's you can solve the problem. And there's not a big deal in the process of solving, just you can replace it. You can, after solving the problem, you can solve uh, the advantage of solving the problems in a parametric way, you can replace it with any numeric value. So, and if you want to go for displacement position, a velocity is change of displacement over time. So if we have velocity already and integrate it, so it just gives us integration from 0 to s ds. If you integrate it based off t, it just gives you s is equal to this function, and if by integrating a negative half, it just gives you a positive half in the power. And displacement is s equal 1 over a zero point 0.4 open bracket this expression, then close it. And it just gives you for t is equal to 4 seconds, s is equal to 4.34. So the initial problem statement was for 4 seconds. So just my bad, just replace the velocity numeric value also. So calculate the numeric value also. It means simply replace a t equal to 3 in the previous part. So that gives us a displacement and as well as a velocity for a projectile. Let's attempt another example. So during a test, a rocket mm, travels upward by a speed of 75 meter per second, and when it is at the height of 40 meters from the ground, uh-huh, the engine fails. We want to determine the maximum height SB, maximum height which the rocket will travel in the positive y direction, uh-huh, and also the speed of the rocket just before hitting the ground, mm, neglecting the air resistance and also the drag effect. mm. So for maximum height solution, if you can consider a 2 point of A and B. mm, We do know the rocket just as soon as the engine fails after 40 meters, it just goes upward by that uh, uh, velocity and or acceleration until it reaches to the velocity of 0. That's the maximum height when it just a climb down the sky to hit the ground. So if you solve it with this simple equation, v squared b minus v squared a, that's equal to 2 times acceleration, a difference between their displacement. So we do know at this stop point, which is the maximum height, is where velocity goes 0. So if you replace velocity at b by 0, and it just simply gives you 0 is equal to bring VA in the other side. That's a 75, positive 75 meter per second squared plus 2 times a downward a acceleration of gravity meter over square seconds time displacement of SB, uh-huh, That's a SA minus SA. Mhm. So that gives you a displacement of x of b or s of b from the origin, which is here, mhm, of a 300 to 70 meters. If you are a picky about what happened here, you can replace it by a just a 9.81 and just goes by SB minus 40. That's they are also identical to each other, and you reach to the same numeric value of 325, 27 meters for the maximum height from the origin. Hmm? Then for velocity, if you velocity just before hitting the ground here, before reaching the ground, it's just v squared c minus v squared b is equal to 2a, the same using the same formula, this time between a b and c. It just gives you v squared c, because vb is again 0, is equal to a negative 9.81 meter per square second times 0 minus 0 minus a 327, which is SB. Hmm? And if you do the math, it just gives you a velocity of c is a downward velocity 80.1 meter per second, and that's a downward. Hmm? Just remember that you can note one, you can solve the also use point between A and C, A and C instead of B and C for calculation of the velocity just before hitting the ground. How is that? That says VC squared, VC squared minus V squared A is equal to 2I, a 2 acceleration times a displacement at C minus displacement at A. Just gives V. A c squared is a VA, which is 25 meter per second square, plus 2 times acceleration times 0 minus 40. 0 minus 40. Mhm. Again, if you are uh, just just use the formula, either work with the direction or acceleration to get the numeric value for velocity at c. And if you do the same, you do it in this way, it just gives you the same 80 point, almost 1 meter per second, like what we have solved before. And at the same time, pay attention to notice too that the rocket is decelerating from A to B by a decelerating from A to B, mhm, by 9.81 meters square second, the gravity acceleration, constant acceleration, and also from B to C, rocket is accelerating from B to C, downward diving, is just with the same rate of 9.81 meter per second. So, however, the rocket at the moment comes to rest at B over here, the acceleration at B velocity is 0, while however the acceleration is still 9.81 meter square second downward in a downward direction, that it just leads to have a higher velocity at C. We'll solve more problem in next videos. Thank you.